Hey, chess enthusiasts and coding adventurers. Welcome to a journey that's been years in the making. Since childhood, I have been fascinated by chess. It wasn't just a game for me, it was a passion that would shape my future. Fast forward to today, I am now 2000 rated player on leeches. But that childhood fascination, it never faded. Instead, it evolved into a new challenge, creating an AI that could outsmart me at my own game. This summer, I finally got the chance to turn that dream into reality. Join me as we deep dive into the worlds of algorithm, game theory, and artificial intelligence. Together, we will build a chess engine from the ground up. Whether you are a chess buff, a coding ninja, or just curious about AI, this series has something for everyone. We will unravel the mysteries of chess strategy, tackle complex coding challenges, and maybe, just maybe, create an AI that can give grandmasters a run for their money. So, are you ready to make some moves? Let's checkmate this challenge and create something amazing together. Let the game begin. Now that we have set the stage, let's dive into the code. Our first step is crucial. We are going to build the chess game environment. This is where all the action happens, where players will make their moves. But here's the key. We are not just allowing any moves. We are focusing on valid moves only. This is essential for creating a realistic and rule-abiding chess engine. Let's start with the foundation, the game state. We will represent our chessboard using a two-dimensional list, or as some might call it, a 2D array. This 2D list will be our virtual chessboard. Each element in this list will store information about what's occupying a particular square, whether it's a pawn, a knight, a queen, or maybe it's empty. Think of it as a digital snapshot of a real chessboard at any given moment. This structure will allow us to easily access and update the state of any square on the board. Now let's dive into one of the most crucial methods in our chess engine, make move. This method is responsible for executing a move on our board and updating the game state. This method takes a move object as an argument. This object contains all the information about the move we want to make. First, we update the board. We set the starting square to empty and move the piece to its new position. We then lock this move and switch the turn to the other player. Next, we have special handling for king moves. If a king moves, we update its location. This is crucial for checking for checks and castling ladder. Now we handle en passant. If a pawn moves 2 squares, we mark the square it passes over as possible en passant target for the next move. If this move was an en passant capture, we remove the captured pawn from the board. For pawn promotion, we are currently always promoting to a queen. In a full implementation, we had allowed the player to choose. Castling is a bit tricky. If the move was a castle, we need to move the rooks as well as the king. We handle both kingside and queenside castling here. Finally, we log the current en passant possibility and update our casting rights. These logs allow us to undo moves if needed. This method encapsulates all the complex rules of chess in one place. It ensures that when we make a move, all aspects of the game state are correctly updated. For example, let's dive into our getKnight moves method. This function is responsible for generating all valid moves for a knight at a given position on the board. The method takes three parameters, R and C for the row and column of the knight, and moves, which is a list we will append valid moves to. First, we check if the knight is pinned. A pinned piece can't move because doing so will expose the king to check. We iterate through our list of pins backward. If we find that this knight is pinned, we mark it as pinned and remove it from the pin list. We will add it back later if it's still pinned after the move. Next, we find all possible moves a knight can make. Remember, knights move in an L shape, two squares in one direction and one square perpendicular to that, like Magnus said. This tuple represents all 8 possible knight moves. We determine the color of the current player's pieces. This helps us avoiding capturing our own pieces. Now we loop through all possible knight moves for each move. First, we calculate the new row and column after the move. We check if the new position is within the board boundaries. If the knight isn't pinned, we check what piece, if any, is on the target square. If the target square is empty or contains any enemy piece, we add this move to our list of valued moves. Notice that if the knight is pinned, we don't generate any moves for it. This is a key aspect of chess strategy. A pinned knight can't move at all. This method ensures that we only generate legal knight moves considering the board boundaries, piece colors, and the concept of pinned pieces. It's a crucial part of our move generation system. Likewise, we will generate moves for other pieces as well. Now that we have gone through the key components, let's see it in action. So let's try out the Ruy Lopez opening. Pawn to e4. It's black's turn. Pawn to e5. Now we take out our knight. Opponent's knight. Now bishop to b5. Now pawn to a6. It's the black's move. Retreating the bishop. Again the pawn push. Again retreating the bishop. So everything looks fine. Let's now try and do some random moves. Oh, here pawn. Taking their piece. Yeah, works great. Taking again. Now let's try and do the castling. Yeah, oops. Great. Everything is working fine. Now that we have seen our chess environment in action, let's dive into the art of our AI, the decision making process. We will start by explaining a crucial algorithm called alpha-beta pruning. To understand alpha-beta pruning, we first need to talk about the Minimax algorithm. In chess, the AI considers possible future moves, creating a tree of possibilities. Minimax traverses this entire tree to find the best move. However, examining every possible move quickly becomes computationally expensive. This is where alpha-beta pruning comes in. Suppose we are evaluating a position and we have found a move that gives white a significant advantage. If we then find an even better move for white, we don't need to consider black's responses to the first move anymore. We know black would choose a different path. By implementing alpha-beta pruning, we can search much deeper into the game tree in the same amount of time, allowing our AI to make better decisions. Moving on to the code for find move Negamax alpha beta, a version of Minimax, we will first check if depth is 0. If yes, we will return the current board evaluation, else we will play each valid move and try to find optimal score through recursively calling the Negamax function for other player. After getting the score, we will undo the moves and will store the next move globally. But our Negamax function uses some kind of score, right, to score the current position. So we will score the current position according to the current piece values of particular player. So we will iterate through all the squares on the board and we'll assign the score to particular color according to their pieces. This is typically a naive solution for current score, but in further versions we will implement some positional play as well. Now that we have explored the inner workings of our chess engine, it's time for the moment of truth. We are going to play a game against our AI. Let's do it. That was a pretty good game by our AI. But currently you are not considering the positional play, right? So to incorporate the positional play, we have to add some different scoring parameters and methods as well. First, let's look at these tables of numbers. These are called p-square tables. We have them for each type of piece, but I am showing the rook and queen tables as examples. Each number represents the value of having that piece on that particular square. For instance, a rook on the second rank in the center is generally more valuable than rook in the corner. Notice how the values for rooks are higher on the 7th rank and in the open files. This reflects chess strategies where rooks are strong in these positions. For queens, we see high values in the center and on the opponent's side of the board, where they can threaten the enemy king. Let's look at our modified score position function. We start with a score of 0 and then iterate over every square on the board. For each piece, we add 2 values to the score. The basic value of the piece stored in our p-score dictionary, which we already saw, and now the position value from our p-square tables. We add this for white pieces and subtract for black pieces. Notice this check for endgame. Chess strategy changes in the endgame, especially for kings, so we use different values in this phase. Upon some UI improvements, our chess engine now looks like this. Let's now try and play a game at higher depth. Final part of our chess engine, we are going to discuss a feature that takes our AI to the next level: opening books. An opening book is a database of chess opening moves. It's like giving our AI a wealth of knowledge from centuries of chess theory and grandmasters games. By using an opening book, our AI can play strong, theoretical, sound moves in the opening without having to calculate them. This saves computational power for middle and end game, where calculation becomes more critical. It also makes our AI play more human-like and diverse in the opening phase of the game. However, it's important to note that we are not blindly following the book. We are choosing randomly from good moves, which adds an element of unpredictability to our AI's play. Instead of me playing against AI, how about the AI versus AI game? Here you go.
I love you もろくに言わない口下手でほんまに不器用なのに さよならは言えたの。ダメだね、ダメよ、ダメなのよ。あんたが好きで好きすぎて、どれだけ強いお酒でも歪まない思い出がバカみたい。バカみたい、ほんとバカね。あんた信じるばかりで強い女のふり、切なさの夜風浴びる。一人になって3年が過ぎ、街並みさえも変わりました。なのにどうして未練だけ置き去り。ほんまにろくな男やない。揃いの指輪外します。ざまみろせいせいするわ。いい加減待っててもバカみたい。
We have come a long way in this video. We started with the basic rules of chess, built a digital board, implemented complex algorithms like alpha beta pruning, fine-tuned our position evaluation, and even added human-like opening play with our book. Creating a chess engine is a journey that combines so many fascinating elements: game theory, computer science, and the age-old strategies of chess. It's a perfect example of how we can teach computers to tackle complex problems. Before we wrap up, I want to give a special shout out to Eddie Sharik and his YouTube channel. His playlist on building a chess engine was invaluable in helping me navigate my ideas and bring this project to life. If you are interested in diving deeper into chess programming, I highly recommend checking out his channel. Remember, this is just the beginning. There is always room for improvement and optimization. Maybe you could experiment with machine learning techniques or fine-tune the evaluation function. The possibilities are endless. I hope this video has inspired you to dive deeper into the world of chess programming, or maybe even start building your own game AI. Remember, every grand project starts with a single line of code, and there are great resources out there to help you along the way. Thank you for joining me on this chess engine adventure. Until next time, keep coding and maybe challenge your computer to a game of chess. You build it after all.